Hello and welcome back to STEAM with Steve. Today we're going to go through a fundamental concept for computer scientists, which is the binary number system. This is an awesome concept which is almost like the alphabet for a computer scientist, and I'll be unpackaging how that sort of looks with a few different tricks up my sleeve. So here we go. So the number system we're going to do is binary. I'm going to unpackage what the learning objectives are for today. So we're going to understand the basic number system, where we're going to focus on binary. We're going to differentiate between data and information. We're going to learn how to convert between Roman numerals, and then also how binary and decimal sort of connect between each other with a little bit of ASCII, and then apply that knowledge to convert analog data into digital format. So the first question you probably have is, how do we actually count? So we've been doing this since we're probably 2 years old, but it's quite important that we sort of reflect how that works, so that when we think of how a computer thinks about it, we can understand what they need to do. So how do we count as humans? It's pretty easy. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, and then we have a 9 character. Now these characters are used and then merged together with the same characters to build different meanings behind them. So once we get to 9, we go up to the next column, which then gives you 10. Now I've color coded this hopefully so that you can see the pattern a bit more obvious. Once we get the 10, we then add on one more, which then gives us 11. Then we get 12, 13, 14, 15, 16, 17, 18, and then 19. And then once we have that, we move up to the next column, which gives us 20, 21, 22, 23, 24, 25, 26, 27, 28, and then 29. And then you should see this pattern grows on itself. So you have the 10s, the 20s, the 30s, the 40s, the 50s, the 60s, the 70s, the 80s, the 90s, and they always have the pattern of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 attached to it. Now that pattern is fundamental of how we count all the way up to 99. And then once we've got to 99, we've exhausted all the different combinations that we can do with those 9 characters. And then that's why we have the hundreds column. And then we go again. So we go have the 1, 100, then 101, 102, and then so on. So the first thing I would like you to do is create your own new number system. But instead of having all those characters, you only can use the 0 and a 1, much like the way that a computer thinks. I want you to try and create a number system from 0 to 5, but you can only use 0 and 1. So please pause the video, have a go, and talk between your friends of what actually happens. Fantastic, welcome back. So the next thing that we need to unpackage, once you've played around with that, is the powers of 2. Now these powers are really important for computer scientists. They help us understand how a computer thinks, which you'll see later down the track. So powers of 2, pretty easy. They're just multiplying by 2 or doubling it. And it starts with 2 to the power of 0. So anything to the power of 0 is always equal to 1. 2 to the power of 1 then is equal to 2. 2 to the power of 2 is equal to 4. Then you have 2 to the power of 3, which gives you 8. 2 to the power of 4, which gives you 16. 32, 64, 128, 256, and then at the end you got 512. Now these are sort of the building blocks of how binary numbers work, which you'll see later down the track when we get a little bit further on. They're really, really important for computer scientists. They're super important. These are sort of the bread and butter. Now you might have thought of seen some of these number patterns before. So for example, Nintendo 64 is based off the 64. Some of your graphics cards or the amount of RAM that you have inside of your computer, you would have seen like a 256 gig hard disk. Those numbers are that way because that's the way that a computer understands them, which is really, really important. So before we lean into the binary numbers, it's really important to understand what the difference is between a character and a number. So if I said the number 3, we have a whole heap of different ways of representing that. We can write it like that, which we're all pretty much familiar. We could write it like the Romans did with 3 lines. You could then write it with the number 3, so the word 3. You could do it the Chinese or Japanese structure with 3 dashes. You could do it with 3 dots, or you could write it like 3 over 1. There's a whole heap of different ways here. Now it's important to understand that these have the same meaning of 3, but they're describing 3 in different ways, because a number believe it or not, is an abstract concept. So it's not quite tangible. We can show three things, like we can say 3 fingers or 3 glasses or 3 PlayStations. There's a whole heap of ways that we can represent it. But 3 by itself is an abstract concept. And we need to understand how a computer might be able to understand what that means. So characters are simply symbols that humans have attached meaning to. A number is an abstract concept, which is really important to know the difference. So leaning into an abstract concept, we have different number systems. So one of the first ones that happened is a Roman numeral structure, which looks something like this. So you had I, which represented 1, you had V, which represented 5, X that represented 10, L for 50, C for 100, D for 500, and then you have the M for 1,000. Interesting enough, you might have heard of centimeters, so C, millimeters, M, that there is a connection there, believe it or not. So if we start, you got the first characters from 1 to 10. The way that the structure works is you have an I for 1, a 2 for 2 I's, 3 for 3, so 3 I's, and then it changes. So instead of doing 4 lines for 4, what they worked out is they can use these characters together and merge them to make different meanings. So you go IV gives you a 4, V gives you a 5, 1 after 5 is a 6, 2 after 5 gives you a 7, and then 3 after 5 gives you an 8. Then, because they can use these characters and make it the same sort of meaning, is you have IX, which gives you 9, and then X, which gives you a 10. By having this structure, it gives you a way of sharing the number system with someone else, and they can understand what you mean. That's why the Romans built it this way. The next column after this, once we get up to 11, builds on what you already have. So now we have 10 plus 1. And what you see is that basically they've done exactly the same pattern as the first column, but they've just jammed an X on the front because there's 10 and then that number. So this sort of introduced the idea of place value all the way up to 20, which is then 2 X's. Then this pattern repeats itself. So then you have 20 on the front and then those numbers all the way up to 30. Once it got to this stage, it's a little bit different. So instead of 40 being 4 X's, the way that we would represent it would be with X and then an L. So the symbols that are attached to it are slightly different. And then that gives it the meaning. So I want you to have a go now with this challenge. I've given you a table here, so you can just look it up if you want. Or, which I prefer, actually try and change these values around by yourselves. So just pause the video here and see if you can work out the values. Awesome. So hopefully you've picked up the first one. So XI gives you 11. So what happens there is you've got a 10 and a 1, which gives you 11. The next one then is 23. So you've got 2 and a 3. XLIV then gives you 44. LXXVII gives you 78. EXCIX then gives you 99. And then we convert the following Roman numerals. So 8 is VII, 42 is XLII, 73 is LXXII, LXXIX is 89, and then CDLXXV is 475. So hopefully you've seen the patterns there. The reason we've done this before learning binary numbers is just to understand that these characters have different meanings, and it's just our perception of what they mean. And different number systems have existed since way, way, way back, and they've always grown in different ways, which is kind of cool to see. So we're going to unpackage a bit of the history of how those numbers have grown. The ancient Egyptians basically did it in groups of 10. So you had ones, tens, hundreds, thousands, 10,000s, 100,000s, and then a million. And the way that they did it was with groups. So if you wanted to represent 100, you would use the little whip. Or if you did 10,000, you would have a candle. So for example, if you had 30,000, you'd do 3 candles. They also introduced fractions, which was kind of cool and really neat. The main numbers is said to be the first group that actually introduced 0, which is really neat. And then what they did is they had dots. So they had 1, 2, 3, 4. And then once you had a group of 4, you would draw a line through it to signify that that was a group of 5. Then you would keep going with the 6, 7, 8, 9 by having the dots. And then once you had another group of 5, you'd do the line. So 10 was actually 2 lines. And then that pattern just repeated for 15, 20, etc., etc., etc. They did it all in groups of 5. Then you had the Chinese numeral system, which had 1 as a line, 2 is 2 lines, 3 is 3 lines, all the way up to 9. And then also this fundamental grouping of tens, hundreds, thousands, and so on. So that structure of using groups of 10s or 5s, and also with Romans, they're on different sides of the world, but they also all use the same sort of structure, which is kind of neat if you think about it. The other one that I found, which is kind of neat, was medieval monks developed this system, the Cistercian digital scoring system. And the way that it works is you could represent a number in a single character. So you would have a straight line, and then branching off it in these 4 quadrants would have the same sort of patterns so that you could see the links. So for example, 1 was just a straight line, a 2 was another line but underneath it, a 3 was a diagonal line, all the way up to 5, and then you had sort of this progression of building a box, which would represent all the way up from 6 to 9. So the top right-hand quadrant represented the ones column, the top left-hand quadrant represented the tens column, the bottom right-hand column represented the hundreds column, and the bottom left-hand quadrant represented the thousands column. And then if you look down the bottom here, like 4,723, the 4,000 is basically this line that comes out in the straight line in the bottom left-hand corner. The 700 is this box right here. The 20 is then this straight line here. And then the 3 is this diagonal line that comes down here, which is pretty cool. So the whole idea of our modern number system actually is built on all these different structures that have come through it. Believe it or not, it's actually originated in Brahmi structure, which looks kind of similar to the Chinese structure as well, which kind of blew me away when I was doing the research on this. So then you have the Hindu system that built on that, which then starts getting some familiar things. So there's a 3 there that looks kind of similar. The 4 looks kind of similar-ish. Then you have the Arabic system, which then changed it a little bit again. Then the medieval system, which is looking really familiar now, apart from the 4, 5, and 7. So the 4 looks like a fish, and then the 5 is upside down, and the 7's a little bit more leaned over. And then you have our modern number system down the bottom there. So these are just characters that represent something. And that's the biggest thing that you need to think about. So how many characters are there in our modern number system? Well, there's 10. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and then all the way up to 9. The question you should be asking is, why do we use groups of 10? Well, the answer is actually right in front of you. So we count in groups of 10 because of our fingers. And you'll see this prevalent in all the number systems that we just looked at. So it goes 0, 1, 2, 3, 4, 5, much like the mind system, and then 6, 7, 8, 9, 10. And see how that's very similar to the Romans as well. So all these number systems that we've had through history are all based on 10 simply because we have 10 fingers, right? So as humans, the answer is right in front of you. You have those 10 fingers, and that's what the groupings happen with that. So our modern number system is built like this with those 10 symbols, 10 characters, and it grows from that, which is a little bit different. So our modern number system, if we think about it, we actually unpackage it. We have the ones column, the tens column, the hundreds column, the thousands column, and then the 10,000s column. But if we wanted to think about the actual math behind that, that's the same as the 10 to the power of 0 column, 10 to the power of 1 column, 10 to the power of 2, 10 to the power of 3, and then 10 to the power of 4. So then, if we unpackage that, what happens is, if we group all these things down, is they're all in groups of 10. So this is the same as 0 times 1. This is the same as 4 times 10 with the tens column. The 100 is the same as 1 times 100, 9 times 1,000, and then 4 times 10,000. And then what we do as humans is we add all those together because we can count in groups of 10, and that's really familiar for us to understand that each part of that sort of links together. Now, if we didn't have 10 fingers, that's where the change in this happens. So instead of doing in groups of 10, for a computer, it actually does it in groups of 2 because they only have 2 options with binary, which is really, really neat. So when we say base 10, that is the number system that we use. So that is the decimal system. Okay. So the number is formed with groups of 10 and uses the following characters that we've done. So if we have 3,267, that's the same as 3 times 1,000 plus 2 times 100 plus 6 times 10 plus 7 times 1. And then that's how it sort of unpackages. So by using these numbers that we have available to us, they branch down like that. This is also known as the denary number system. Some may have heard of it as that. So what characters can a computer only understand? Well, hopefully I've alluded to that already for you. They can only understand 0 and 1. So that this is what binary means. So it understands 0 or 1 or true or false, which is what the binary number system is. So this is also known as the base 2 system. So when we use the characters in base 10, we can use all 10 characters because of the 10 fingers that we have. A computer can only use the 0 and the 1, which is a little bit different. So how do
This might answer your question. 0 plus 1 is 1.
Thanks, Alexa. No thanks. So how do you count to 3 in binary? Sorry about that. You have these usable characters. So you go 0, then you go 1, then 2, then 3. And then in the binary system, what happens if we think about it, we can only use the characters 0 and 1. So this grid hopefully will help you look at that. So 0 in base 2 is actually exactly the same. It's just 0. 1 in base 2, again, you can use a 1, so it's all fine. The first one that's really hard is a 2. So you can't actually use that character because it's illegal. A computer can only understand 0 and 1. So what happens is it becomes 10, then 3 becomes 11. Okay? Because what happens then is you can use those characters. And if you think about it, what happens with 10 is you have 1 in the 2's column and then 0 in the 1's column, which was where we're sort of going with this. Pretty cool. So you can use the 3, can't use any of those characters, but we can use the 10. We can then use the 11. We can't use 12, and so on. So there's a bit of a bad joke for you. There's 10 types of people in this world, those that understand binary and those who don't, which again means that there's 2 types of people. So 10 in binary is 2, basically. So how do we count to 5 in binary? Same process. So we only have these usable characters, and which is 0 and 1. So 0 again, exactly the same, is 0. 1 again is the same. 2, we can't use the 2, can't use the 3 that we traditionally know, or 4, but we can use 10. 3, we can use 11, but then when we get to 4, it is actually 100. And then if you look at the columns behind it, you have the 1's column, the 2's column, and then the 4's column, which is kind of neat. Then when we get to 5, it's the same as 100 plus 1. And what you should see is there's this pattern that's happening where it's oscillating between 0 and 1. You're just jamming 1s on the front, basically, which is kind of cool. So you can't use the 3, 4, 5, 6, 7, 8, 9. They're all illegal. Can't use those. Can't use all these numbers in the middle here. But when we get towards the end here, we can use 100 because the computer can understand 0 and 1. We can use the 101 because that represents 5. That's the next character that we can do. We can't use the 102 or 103 for the next step. So if we want to count all the way up to 10 this time, so we're going to go from 0, 1, 3, 4, 5, 6, 7, 8, 9, 10. What happens is the pattern works sort of like this. So we can have a 0, we can have a 1, then we can have a 10, then we can have 11. After that, we've gone to the next group of columns. So we're up to the hundreds column, or the 4s. And then you've got a 4 plus 1, which gives you 5. Then you have 4 plus 2, which gives you 6, which is what the 110 represents. Then we get up to 7, which gives us 111. So we're kind of getting towards the end of that group, right? So then we have to move on to the next column, which is what the eights column is. So then we go way back to the start again and we get 1,000. So that's the next character set that we can use. Then for 9, it's 1,000 plus 1, which gives you 1,001. And then for 10, it becomes 1,010. So for a computer to understand it, remember it can only use the zeros and ones, but there's a pattern that happens behind it, which is what this does. Cool. So the next part then is we're going to look at an easier way to sort of understand how to get this connection, which hopefully will be a little bit easy for you to sort of see the pattern. So how the binary number system actually works is the columns. So when we look at a number like this, 11001, what happens is we have the ones column, it's exactly the same as what we're used to, but this is where it gets a little bit different. Instead of the tens column, we now have the twos column. So it will either have a 2 or it won't have a 2. You'll then have the fours column. So you either have a 4 or you won't have a 4. You'll have the eights column, and then you'll have the 16s column. So like I said, these are the really important numbers for computer scientists. And if we think about it, this is the same as 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and then 2 to the power of 4. So to convert this number into a number that we understand in decimal, it's pretty easy. Basically, we just have to flow down. So we go, that's the same as 1 lot of 1. We've got no 2s, we've got no 4s, we have an 8, we have a 16. So then, if we add all those numbers together, what happens is you have 1 plus 8 plus 16, which then gives you 25. So the idea behind this, 11001, is what a computer would understand to be 25. So my advice to you when you're starting off with this is to draw the table and maybe have the powers of 2 above the number. So have the 1, 2, 4, 8, 16, 32, and so on. And then that makes that conversion a whole heap easier for you. So if we're trying to convert between these numbers, what you will see, 0 is still 0, 1 stays there and becomes a 1. 2 then becomes you have one group of 2, so that's why it becomes 10. 11 is the same as one group of 2 plus 1, which is why it's 11. 4, see how that's a power of 2, so then you move on to the next column. So that's why it becomes 100. Then, this is the really cool part, is you should see the pattern replicated now. So those first 4 numbers that you see there, 0, 1, 10, 11, basically will now repeat. So now instead of 100, you'll have 101, 110, and then 111. Once you get to that point, you're now up to the next group. So that's why you're up to 1,000. Then all that pattern that you see before it repeats. So now you have 1001, 1010, 1011, 1100, 1001, 1010, 1011, and then look at that, 16 power of 2 becomes 1, 0, 0, 0, 0, 0. Then the pattern keeps going on. So you have the 1 on the end, 10, 11, 12, 100, 101, 110, 111. Then you go back up to 1100, which is the same as 8 plus 16. If you're thinking about, because these are either on or off. And then that pattern keeps going all the way up to 32, because then that's the next group of power of 2. Then what happens is exactly the same now, is we have 1 with all those other numbers that we've just had before it, repeat itself all the way up to 64. And then once we get to 64, so 63 is one number before, so it's all on, 1, 1, 1, 1, 1, and we get a million. And then 65 is a million plus 1, because you've got one more on. And then this is exactly how our computer will think. It's either on or off, which is really, really, really cool. So when we think of base notation, decimals will always have 12, and then binary version, that would be 110, so 8 plus 4. So the notation is you basically put a little 10 at the end for when it's in base 10, and then you put a little 2 when it's base 2 at the back. The small number describes the base. So the last challenge I want you guys to have a crack at is basically convert these numbers between decimal and binary. So I've made a little grid up the top here with the powers of 2, so you can see where the column is. Pause the video here and then have a crack and see if you can convert these using the powers of 2 that you can see. My advice is basically if there's a 1, it means it's on, so you have it, and if it's a 0, you don't have it. So it's this starting to understand on and off. Awesome. Hopefully you paused the video and you had a crack. So the first one with 11 is the same as 1 times 2 plus 1 times 1. So you have 2 plus 1, which then gives you 3. The next one then is you've got 1 plus 4 plus 0 times 2 plus 1 times 1, which then gives you 5. Then you have 1 times 8 plus no 4s, no 2s, plus a 1, which then gives you 9. The next one then you have an 8 plus a 4, so that gives you 12. The next one then you have a 16 plus a 2, which gives you 18. Well, next one you then have is 32 plus 16 plus 8 plus 1. And the last one is a little bit more trickier. You have a 256, you have a 32, you have an 8, a 2, and a 1. So the first one, if we look at that, would give us 3, because you have 2 times 1 plus the 1. Then you would have 5, then you would have 9, then you would have 12, then 18, 57, and then 299 at the end. Cool. So there's some conclusion questions to think about when you finish it. Is how does understanding binary help us appreciate modern technology? In what ways can we use this with the character sets that we'll be eventually doing? And then discuss a scenario where it's necessary for converting the data from analog into this digital that you've sort of worked on. There's a Kahoot there. Have a go. The link's in the bio down below. Hopefully that gives you some overview of what has to happen within binary. So hopefully if you enjoyed this, really enjoyed going through binary. It's one of my favorite things to teach. Just really important, just remember it's on and off. So it is a bit of a mind game that you need to sort of think about, that you can only use 0 and 1. So thanks again. Hopefully you enjoyed. See you next time on STEAM with Steve.